Metrics. It's incredibly important that we evaluate our work. We'll start with the confusion matrix, where we're going to look at false positives, false negatives, true positives, and true negatives in the confusion matrix. So metrics analyze algorithms' behaviors. They analyze algorithms that produce outcomes without prior assumptions about the data. So metrics relate a classifier to the process that produces the data, ideally without relying on the data itself. Metrics tell us if a given set of data is capable of answering the question we're asking. And they can be used to reject a model. We'll never be forced to accept a model. So let's begin with binary classifiers, which you remember are classifiers with two classes, 0, 1, positive, negative, true, false. We'll do multiple classes later. We're going to suppose our data has capital P positives and N negatives. The binary classifier labels little p observations as being positive and little n observations as being negative. So capital P and capital N are counts of actual, little p and little n are counts of predicted. So let's look at some extremely bad classifiers. We could classify every observation as positive. And this would be the totally positive classifier. It would mean the little p is capital P plus n and little n is 0 because everything's classified positive. Totally negative classifier is similar. We could also do a coin toss classifier. Rather than consider the data at all, we simply, for each observation, flip a coin. We predict that an observation is positive if we get heads and negative if we get tails. So what's going to happen? About half of the data will be predicted positive. So little p is approximately 1/2 capital P and little n is approximately 1/2 capital N. So possible outcomes of a binary classifier: we could have true positives and true negatives. We could have false positives, observations that are actually negative, but that the classifier labels as positive. And we can also have false negatives. For our notation for these, TP for the number of true positives, TN for the number of true negatives, FP for false positives, and FN for false negatives. So let's look at some examples. Let's go to our extremely bad classifiers. The totally positive classifier predicts everything as positive. So therefore, the true positives is capital P. All the positives are correctly predicted. The false positives are N, since all the negatives are predicted as positive. So true negatives and false negatives are both 0. The coin toss classifier: every positive has a 50% chance of being predicted positive. Every negative a 50% chance of being negative. So true positive is 1/2 of the positives. True negatives are 1/2 of the negatives. False positives 1/2 of the negatives. False negatives 1/2 of the positives. So let's look at our first metrics: accuracy and error. For a classifier that predicts little p in positives and negatives respectively, for a data with capital P in positives and negatives in reality, little p is true positives plus false positives, little n is true negatives plus false negatives. Capital P is true positives plus false negatives, and capital N is true negatives plus false positives. Accuracy is therefore the true positives plus the true negatives over the sum of the positives and the negatives. Error, false positives plus false negatives over capital P positives plus negatives. So these are actually familiar concepts. For instance, a totally positive classifier is going to have an accuracy of about P over P plus N. The error is going to be N over P plus N. So for example, let's look at the coin toss classifier. How accurate will our coin toss classifier be? About half of the positives are labeled correctly. So true positives is 1/2 P. True negatives is 1/2 N. About 1/2 P plus N is correctly labeled out of the P plus N total. So regardless of the sizes of P and N, the accuracy is about half, which is 50%. So the accuracy with our formulas, about 1/2. Now these are what are called edge cases, these extremely bad classifiers. Let's look at what we call tunable binary data, where we can actually tune it so that it's varying degrees of difficulty. So we're going to look at tunable binary data. To do so, the curve y equals cosine squared n pi x for n a positive integer over the interval 0, 1. The area under that curve is equal to 1/2 for every positive integer n. And it's also in the unit square, which has an area of 1. So a point chosen at random in the unit square is equally likely to be either above or below the curve. So equally likely above or below for any n. But if for n large, you get this kind of stacking up property. So our data is points xy chosen uniformly randomly in the unit square, 100 points in the training data, 100 points in the testing data, positive if cosine squared of n pi x is greater than y, negative otherwise. So about half the training and testing sets are positives, and about half the training sets and testing sets are negatives. And notice that any algorithm for a large n is going to have to learn to trust vertical neighbors more than horizontal neighbors because of that stacking property. So here's what training and testing sets look like. So in the blue is the training, and in the black is the testing. The pluses are positives and the minuses are negatives. There's the curve, so you can see the relationship. Here we're doing n equals 4. So if we just look at the test set, assuming we've already trained our classifier, then in the test set we have 52 positives and 48 negatives. And you can see them there. So if we do a one nearest neighbor classifier, train on the training set, that's a 1 in n classifier, then we apply the metrics to the actual test set. We notice that we have a lot of pluses below the curve and a lot of minuses above the curve. This is because of the training data. Remember, we're using the nearest neighbor, and so there's often points below the curve whose nearest neighbor is above the curve, and vice versa. So our little p is 59 predicted positives. Little n is 41 predicted negatives. So we're focusing here on the test set. So the true positives are 43, the false positives are 16. So you can see the false positives here in the shaded green. We have 32 true negatives and 9 false negatives. So the accuracy, true positives plus true negatives over p plus n, that's 43 plus 32 over 52 plus 48, so 75% accuracy. The error is 25%. Now our goal is to test how good at predicting positives. How good are we at predicting positives using true positives, false negatives, and true negatives? And we usually arrange these in a table called the confusion matrix. So we have predicted across the top and actual down the left side. So the sum of the first column is little n, the sum of the second column is little p, the sum of the first row is capital N, the sum of the second row is capital P. So let's look at the example with the tunable binary data we were looking at. If we arrange it in a table, then we see we had 43 true positives, 16 false positives. That's 59 for the little p. So 32 true negatives, 9 false negatives, 41 for the little n, and 48 and 52 for the capital N and P respectively. So how do we handle this confusion matrix? Well, these are useful, these true positives and false positives and such, but typically we don't use them as is, we use them in ratios, i.e. rates. For example, accuracy and error are percentages, they're rates, they're fractions. There are some other useful rates. For instance, the true positive rate is the number of true positives over the number of positives. This is also known as sensitivity or recall. The false positive rate is the number of false positives over the number of negatives. So the true positive rate is called the sensitivity of the classifier. It's an estimate of the probability that a positive observation will be classified as positive. High sensitivity means there's a low likelihood of missing an observation in the positive class. The true positive rate is also called recall. In other words, the fraction of observations that are positive that are recalled as positive. And ideally, our classifiers would be of this form: no false positives or false negatives, P true positives, and N true negatives. But in reality, we're never going to have that kind of perfection. So we're always going to be off by some small epsilon that's small in comparison to N, and some delta that's small in comparison to P. So in reality, we want this where confusion matrix where the epsilon and the delta are small with respect to the N and P respectively. So look at the true positive rate. It's going to be 1 minus delta over capital P. And it's approximately 1 if delta is small with respect to P. The false positive rate is epsilon over N, and it's close to 0 if epsilon is small with respect to N. So the totally positive classifier has a fantastic true positive rate of 1. But the false positive rate is also 1, and that's rather horrible. A coin toss classifier, true positive rate of 0.5, and a false positive rate of 0.5. So notice we've not said anything about epsilon in comparison to P or delta in comparison to N, at least not yet. So our example for the tunable binary data, the true positive rate was about 82.7%. That's pretty good. But notice the sensitivity of 82.7%, or the recall, is good, but the false positive rate is 33%. That's not close to 0. So here's actual data or code producing the confusion matrix. So we did a k nearest neighbors classifier with one neighbor. Then we used a confusion matrix from scikit-learn metrics. So notice we have training, and but when we test on the testing data. So the confusion matrix is the testing actual followed by the testing predicted. Then we can form the true positive, false negative, and true positives, and then finally get those rates. So what about some statistics here? Well, notice that capital N is Tn plus Fp and capital P is Tp plus Fn. The sensitivity, for instance, the true positive rate is Tp over P, which is the same as Tp over Tp plus Fn. So we're going to look at some basic metrics. First, the sensitivity or recall, that's the true positives over the sum of the true positives plus the false negatives. The specificity, true negatives over true negatives for false positives. Accuracy, we've already looked at that. And then these two that we don't use that often, the negative and positive predictive values. Specificity is the true negative rate. True negatives over true negatives plus false positives. The false positive rate is related. Notice we do this calculation, Fp over N, Fp over Fp plus Tn. That means if we add a Tn and subtract a Tn, we get 1 minus the true negative rate. So the false positive rate is 1 minus the true negative rate. So the true negative rate is 1 minus the false positive rate. So high specificity means a classifier rarely misses negative outcomes. So a prediction of positive is a highly reliable result. Precision is also important. It's the true positives over the number of true positives plus false positives. So precision is the fraction of observations classified as positive that are actually positive. So compare it to recall, which is also sensitivity. So precision is important because our goal, remember, is we want epsilon and delta to be small relative to p. So the true positive rate, we saw that the true positive rate is 1 if delta is approximately 0 relative to p. And precision, if we divide the numerator and denominator by the true positives, then we see that we get 1 over 1 plus epsilon times the quantity p minus delta to the negative 1. That means that precision is approximately 1 if epsilon is approximately 0 relative to p. So, for example, the precision for the totally positive classifier is p over p plus n. That means if p is approximately n, then the precision is about 1/2. The coin toss classifier, precision is true positives over true positive plus false positives, 1/2 capital P over capital P plus n. So if p is approximately n, the precision is only 1/4. So in our tunable binary classifier, the precision was about 72.9%. So there's also the F1 metric and the F beta. These are important because both recall and precision are important quantities. Recall is the rate at which a classifier rates positive samples as positive. Precision is the rate at which a classifier does not label as positive a sample that is negative. So the F1 metric, the F1 score, is the harmonic mean of precision and recall. So the F beta is a weighted harmonic mean of precision and recall. And finally, all of this can be done with multiple classes. So the confusion matrix for n labels has n rows and n columns. The predicted labels across the top and the actuals down the left. And we've got TL1, that should be a TL2 down to TLN. These are the true labels, and the F's are the false labels. So we can use lowercase p's for the counts of the predicted, and uppercase p's for the counts of the actuals for each label. So in summary, we have these very important metrics: accuracy, sensitivity, recall, false positive rate, specificity, precision, and again, recall.